Hello, this is Rick from MathX, and today we'll be solving a different kind of problem. Usually on this channel, we solve problems from major math competitions, like AMC 8, AMC 10, Math Kangaroo, Amy. But this problem was actually requested by one of my coaches, Mr. Richard Olson of Eastern Mass ARML. And he sent me this problem saying it was an interesting problem. And after doing it and attempting it for myself, I realized it is quite interesting. As even though it looks quite intimidating at first, it isn't that bad. And if you work smartly and be organized in your work, you can solve it, no matter where you are in math. So it's for that reason I would like to go over it today. Without further ado, let's just get right into it. One of my favorite t-shirts says the following. Only smart people can read this. It does not matter in what order the letters in a word are in. The only important thing is that the first and last letter be in the right place. The rest can be a total mess, and you can still read it without a problem. This is because the brain does not read every letter by itself, but the word as a whole. That is the phenomenal power of the human mind. The quote, starting with it, contains 72 words, and I bet you can still read it. There are 35 words with 3 or fewer letters, 15 4-letter words, 12 5-letter words, and 10 words with 6 or more letters. Without changing the order of the words or the punctuation, if the letters of each word, except for the first and last, are randomly arranged, there are many versions of the shirt. The probability that all the words would be spelled correctly is 1 over 2 to the A times 3 to the B times 5 to the C times 7 to the D. Determine the ordered quadruplet A, B, C, and D. Now, first off, this is a kind of fun problem just to look at, even without solving it, because this quote, it teaches you a little bit of science too. But still, we still have to do the math part of it. So let's think about this. There are 35 words with 3 or fewer letters, 15 4-letter words, 12 5-letter words, and 10 words with 6 or more letters. And in the question, they want us to refrain from changing the order of the words or its punctuation, but only rearrange the letters of the words except for the first and last letter. So, in the case of a word like does, they don't want us to move around D and S. They just want us to move around the E and O. And in the problem, they tell us that the probability of the words being spelled correctly is 1 over 2 to the A, 3 to the B, 5 to the C, and 7 to the D. And then what they want us to find is the ordered quadruplet A, B, C, and D. So essentially what we have to find in this problem is the complete probability, because it gives us a partial part of the probability, but doesn't tell us what degree of 2 is in there, what degree of 3 is in there, what degree of 5 is in there, and what degree of 7 is in there. And we have to find that out for ourselves. So probability is the total number of favorable outcomes over total number of outcomes. In this case, a favorable outcome would be one in which all the words are spelled correctly, and then 2 to the A, 3 to the B, 5 to the C, and 7 to the D. That just represents the number of ways we can write this phrase, rearranging all the letters in the middle of words. So let's think about this. In this case, the favorable outcome, as I said before, is the number of ways this entire quote spelled correctly. But in order for the entire quote to be spelled correctly, each of the words has to be spelled correctly. So, does has to be spelled correctly in one configuration. Matter has to be spelled correctly in one configuration. What has to be spelled correctly in one configuration. And these all have to be in only one configuration, because a word doesn't have 2 different spellings. So, each of these words can only have one spelling. So, does has one, matter has one, what has one, order has one, letters has one, and then all these ones, we have to multiply them all together because these are all independent of one another. So no matter how many ones there are, It's just 1 times 1 times 1 times 1, and it's just going to be 1. There's only one way for all the words in this quote to be spelled correctly. So that limits the top part. Now, as for all the ways the letters inside the words can be rearranged incorrectly or correctly, well, that's the real part of the problem. And that's what we're going to have to find in order to find the powers of 2, 3, 5, and 7. So I think the best approach in this problem would be to take it by a case-by-case basis. So let's start with the first case. 35 words with 3 or fewer letters. Now to start off with, a word always has to have at least one letter. Like there's no word with -3 letters or -1 letter. And along with that, if a word has 0 letters, it's just an empty space. So these words will have a minimum of 1 letter. Now let's think about it. The question tells us that we can't change the order of the first and last letter. So if the word's like A, we can't change it at all because there's nothing to change it with. There's only one letter, so all single letter words are going to stay exactly the same. What if it's a 2-letter word like B? Well then, we have to keep the first and last letter in the exact same spot. So B is forced to be in the beginning spot, and E is also forced to be in the final spot. So once again, there's nothing we can do to B. B has to stay the same. And then we've seen that with A, we can't change it at all. B, we can't change it at all. These words are automatically going to be correct because we can't rearrange any letters inside the word. So then now for a 3-letter word. What's a 3-letter word in this? Not. The first letter has to stay the same, so the first letter has to be N, and the final letter has to be T. So the only letter we can rearrange is O. However, we can't move O to the left of N or to the right of T, because then N is not the first letter and then T is not the final letter. O can only stay in the middle of these two letters, so O has to be in one spot. Thus, there's no ways to rearrange the letters in this word. So all the 35 words with less than or equal to 3 letters, they're just going to stay the same. There's only one way to write these words. So in the end, out of the total number of ways we can write these, this is 1, so it doesn't contribute to this at all. So we can completely ignore this case because this case won't have any rearranged spellings of 3-letter words or less than 3-letter words, because there's just not simply enough letters to rearrange with one another. The next case is the 15 4-letter words. Now, let's look at an example of a 4-letter word. In this case, raid, which is supposed to be read. So, in the case of a 4-letter word, the first and last letters can be stuck in place, and then we can rearrange the middle 2 letters in 2 factorial different ways. And 2 factorial is just 2 different ways. We could put the A first and then the E second, or the E first and then the A second. And as long as there's no duplicate letters, it's always going to be 2 different ways. So then we have to look over all the 4-letter words and see if there's any duplicate letters. The first one is does. Does has an E and an O, no duplicate letters, so there's still 2 ways to rearrange them. What, also, 2 different letters, A and E, 2 different ways to rearrange them. Word, well, R-O-O-R, only 2 letters, 2 different ways to rearrange it. And then as we go on and on like that, we realize none of the 4-letter words have duplicate letters, so all the 4-letter words have 2 different ways to rearrange their letters, keeping the first and last letters the same. And these 2 different ways to rearrange them are the 2 letters in the middle. So 15 different words have 2 different ways to rearrange the words themselves. So it just comes down to 2 times 2 times 2, 15 times. And these 15 times are for each of the 15 different 4-letter words. So the number of ways that we could arrange the letters, 15 4-letter words, without changing the places of the first and last letters is 2 to the 15th. So the next case, 12 5-letter words. So an example of a 5-letter word in this case would be first, which in this case is spelled as frist. Well, in the case of first, keeping the first letter in the first position and the last letter in the final position, we're left with 3 different letters in the middle. Now these 3 different letters can be arranged in 3 factorial ways. There's 3 different letters that can go in the first place, 2 different letters that can go in the second place, and 1 letter that can go in the final place. 3 times 2 times 1. Well, 3 times 2 times 1, 3 factorial, is just equal to 6. So there's 6 different ways to rearrange the letters in the middle of a 5-letter word if all the letters are different. If we look at all the 5-letter words in the passage, we realize that their middle 3 letters are all different. So each of them have 6 different ways to rearrange the letters in the middle. Since there's 12 words, it's 6 times 6 times 6, 12 times. So it's 6 to the 12th different ways to rearrange the 3 different letters in the 12 5 different letter word. Now we're on to the final case, but this is probably our largest case. The 10 words with 6 or more letters. Okay, so unlike all these other cases where we could just take an example and we could check the pattern with each of these examples and then check if all the other words match the pattern, the 10 words with more than equal to 6 letters, well, all these words are different from one another. So we have to set up 10 cases to represent this one general case. So we have to pick out all 10 of the words with greater than equal to 6 letters. So I'll just quickly do that, and we can analyze each and every one of them to see how many different ways we can rearrange the letters in each of those words. Okay, I finished listing out all the words down here, and I've also circled them in the original quote. So as you can see, the words we're searching for, and we're going to check the cases are matter, letters, important, letter, without, problem, because, letter, itself, and phenomenal. So these cases are all special because just like in these two cases, we didn't have to worry about identical words. In all of these cases, we have to worry about identical words. For example, this first word, matter. The number of ways we can rearrange the 4 letters in the middle is not 4 factorial because the t can be counted twice. So it's 4 factorial divided by all the ways we can rearrange the t's. And rearranging the t's with one another, that's 2 factorial ways. So the total number of ways to rearrange the 4 letters inside matter is 4 factorial divided by 2 factorial. 4 factorial is 24, and 2 factorial is 2. So that gives us a total of 12 ways to rearrange the 4 letters inside matter without moving the M or the R. Next one, letters. Once again, they're duplicate letters. We have 2 T's and 2 E's. These 2 T's can be rearranged 2 factorial different ways. These 2 E's can be rearranged 2 factorial ways. And these 5 letters total can be rearranged 5 factorial ways. So the total number of ways to rearrange all 5 of these letters with these duplicate letters is 5 factorial divided by 2 factorial times 2 factorial. 5 factorial is 120, and 2 factorial are each 2. So it's 120 over 2 times 2, which is the same thing as 120 over 4, which is 30, because 120 divided by 4 is 30. Next was important. When we look at the letters inside important, we realize all these letters are distinct from one another. There's no duplicate letters. P is unique, R is unique, M is unique, O is unique, A is unique, T is unique. Well, T is not unique, but we're not going to move this other T. So T is unique within all the letters we're going to move. Because remember, we're keeping I and T the same because they're the first and last letters. The first and last letters must be in the same spots. So out of all the letters we're going to move around, all the letters are unique. So we just need to count out the number of different letters there are, and then we can just find factorial that many ways. So there's 7 different letters inside important, excluding the first and last letters. So that means there's 7 different letters to place in the first spot, 6 different letters to place in the second spot, 5 different letters to place in the third spot, 4 different letters to place in the fourth spot, 3 different letters to place in the fifth spot, 2 different letters to place in the sixth spot, and 1 different letter to place in the final spot, leaving 7 factorial different ways. And 7 factorial is just 7 times 6 times 5 times 4 times 3 times 1, which is also 5040. Our next one is letter. Once again, there's only 4 different letters we can move, but there are 2 pairs of duplicates. So it's 4 factorial divided by 2 factorial ways we could rearrange the t's, and 2 factorial ways we could rearrange the e's. So 4 factorial, because that's the total number of letters, divided by the 2 factorial different ways we could rearrange the t's, also further divided by the 2 factorial different ways we could rearrange the e's. So 4 factorial is 24, 2 factorial is 2, and 2 factorial again is 2. 24 over 2 times 2, which is 24 over 4, which is the same thing as 6. Next one is without. So, for keeping the first and last letters the same, we have to look at all the ways we can rearrange the letters in the middle. O-U-T-H-I. Once again, all these letters are unique, so we can just represent this number as the factorial number of letters. How many letters are there? 1, 2, 3, 4, 5. So that means there's 5 different letters that can go in the first spot, 4 different letters that can go in the second spot, 3 different letters that can go in the third spot, 2 different letters that can go in the fourth spot, and 1 different letter that can go in this final one spot. So it's just 5 times 4 times 3 times 2 times 1, 5 factorial, which is also equal to 120. Next word is problem, rearranged as porbellum. Well, once again, we look at how many different letters there are because all the letters inside between P and M are unique. So O is unique, R is unique, B is unique, E is unique, and L is unique. So that means there's 5 different letters to place in the first spot, 4 different letters to place in the second spot, 3 different letters to place in the third spot, 2 different letters to place in the fourth spot, and 1 different letter to place in the final spot. So 5 times 4 times 3 times 2 times 1, also 5 factorial, which also gives us 120. Now we're at because. Once again, no duplicate letters within all the letters we're going to move. There's an E here, but we're not going to move this other E. So this letter is basically unique to us. So there's 5 different letters we can place in the first spot, C-U-S-E-A. 4 different letters we can place in the second spot, whatever we didn't use the first time. 3 different letters we can place in the third spot, 2 different letters we can place in the fourth spot, and 1 different letter we can place in the final spot. Once again, giving us 5 factorial different ways to rearrange the letters, excluding B and E. Next is letter again. Well, we've already found out the number of ways to rearrange the letters, excluding the first and last one, in the word letter, so we don't have to do that again. We found this time it was rearranged 6 different ways, and this one is just one of the many different permutations of doing it, but it's still the same word, so there's still the same number of rearranging the number of letters. So since we got it a 6 the first time, we get a 6 the second time too. So there's 6 different ways we could rearrange the middle letters, excluding L and R, in the word letter. Now we're on to itself. So itself, keeping I and F in the same spot, there are 4 different letters. So 4 different letters that could go in the first spot, 3 different letters could go in the second spot, 2 different letters could go in the first spot, and 1 letter could go in the final spot, giving us 4 factorial ways. So 4 times 3 times 2 times 1. Now that's just 24. And we're on our final word, phenomenal. So we have to keep P and L in the same spot. So we have to find out all the different ways we could rearrange H through A. So this time we have some duplicated letters and then some non-duplicated letters. So out of all these letters, there's 1, 2, 3, 4, 5, 6, 7, 8 letters different total. So we have 8 factorial. We have to divide it by the number of duplicated letters. So in this case, we have A is duplicated twice because there's 2 A's. So there's 2 factorial different ways to rearrange these 2 A's with one another. And then N is also duplicated. So there's 2 factorial different ways to rearrange these N's amongst one another. So we got 8 factorial divided by 2 factorial times 2 factorial. Now some quick math just tells us 8 factorial is 40,320. And each of these 2 factorials is 2. So it's 40,320 divided by 4, which is simply 10,080. So these are all the different ways we could rearrange the letters in each of the 10 words with greater than equal to 6 letters. So we found out all the different ways to rearrange the letters in each of the different words. We found that with words less than less than or equal to 3 letters, there's only one way to rearrange it. And the first and last letter is the same. With the 15 4-letter words, we found out that each of these 15 4-letter words, well, there's only 2 ways to rearrange it. So there's 2 times 2 times 2, 2 to the 15th different ways we could rearrange all 15 4-letter words, the letters, excluding the first and the last one. For the 12 5-letter words, keeping the first and last letters the same, there's 3 factorial ways we could rearrange the letters in the middle for each of the 5-letter words. And since there's 12 of them, it's 3 factorial to the 12th. 3 factorial is equal to 6, so it's 6 to the 12th. And then with the 10 words greater than or equal to 6, we found for each of these independent cases. So since all of these cases are independent from one another, we have to multiply that, and then we're going to get the total number of cases in which we could rearrange the letters of any of these words without moving the first and last one. So multiplying all these numbers out, we're going to get some really ugly number. But since we only need the prime factorization, we need to take the prime factorization of all the 10 words with greater than or equal to 6 letters and the 12 5-letter words. Because the 15 4-letter words, we already have the prime factorization to that. That's 2 to the 15th. And the 35 words with less than or equal to 3 letters, those are negligible because that's just 1. So we don't even need to, as I said before, we can just ignore that. So the 5-letter words, the 12 5-letter words, it's equivalent to 6 to the 12th. So the prime factorization of 6 to the 12th is 2 to the 12th times 3 to the 12th. So that's because the prime factorization is 6 is just 2 times 3. So if we raise 6 to the 12th, we just have to raise both these to the 12th too. The prime factorization of 12 is 2 squared times 3. Prime factorization of 30 is 2 times 3 times 5. The prime factor of 7 factorial is a little harder to get, but remember, just break it up. How many 2's are in 7? There's 2, 4, and 6, but then 4 has 2 2's, so that gives us 2 to the 4th. How many 3's are there? There's 3 and 6, so that gives us 2 3's. There's 1 5, and then there's 1 7. So that's the prime factorization of 7 factorial. 6, the prime factorization of 6 is just 2 times 3. The prime factorization of 120 is 230 times 3 times 5, because that'll give us 8 times 15, which is 120. 120 again, 2 to the 3 times 3 times 5, and 120 again, 2 to the 3 times 3 times 5. The prime factorization of 6, once again, is 2 times 3. The prime factorization of 24 is 2 to the 3 times 3, because 2 to the 3 gives us 8, and 8 times 3 is 24. And then 8 factorial divided by 2 factorial times 2 factorial. Well, that's the same thing as 7 factorial times 2. 7 factorial we deduced to be 5040. And 10,080 is twice as much as 5040. So 10,080 we just have one extra 2 than the prime factorization of 540. So instead of having 2 to the 4th, it would be 2 to the 5th. So the prime factorization of 1080 is just 2 to the 5th times 3 squared times 5 times 7. So now, multiplying this all out to get our total number in terms of 2 to the A, 3 to the B, 5 to the C, and 7 to the D, we just need to group all the 2's together, all the 3's together, all the 5's together, and all the 7's together. So when we go down, multiply all these numbers out, we get our numbers to come up to 2 to the 55 times 3 to the 24 times 5 to the 6 times 7 to the 2. So we get that this is the total number of ways to rearrange the letters in all the words in this quote without changing the first and last letters' places and without changing anything else. So the probability would be 1 over 2 to the 55, 3 to the 24, 5 to the 6, and 7 to the 2. Because as I said before, there's only one way for all the words in this quote to be spelled correctly. So we can see that our quadruple A, B, C, and D is just 55, 24, 6, and 2.